these. Let's go ahead and take a look. This is just similar to what we did yesterday. Find the size that's exactly between the two numbers. To do that, we add them and then divide by 2. So here we have 5/8 and 3/4. Add those, we need a common denominator, which is just going to be the 8ths. So 5/8 doesn't change. 3/4, well, it's 4 times 2 to make 8, so 3 times 2 is 6. That's 6/8. We add the 5 and 6 to make 11/8. Now, as we mentioned yesterday, this is an improper fraction. And if this were our final answer, we would be reducing it to a mixed number. But since we're going to continue calculating with it, it's often easier if we leave it as an improper fraction, because our next step is going to be to divide by 2. And of course, to divide by 2, we have to turn the 2 into a fraction. We make it 2/1. And then we do the change to multiplying by the reciprocal. So we multiply by 1/2, giving us 11/16. Now these next two, I added a little twist from yesterday. Rather than just being the fractions, I put a whole number in front of them. So with the first one here, we have 1 and 5/16. Then we're going to add that to 1 and 3/8. Now my common denominator there is going to be the 16. The 5/16 just stays 5/16. For 3/8, it takes 8 times 2 to make 16, so 3 times 2 is 6. We add 5 and 6 makes 11/16. 1 and 1 makes 2. And now again, that has to be divided by 2, and we'll make it 2/1 right away. Now that 2 and 11/16 is a mixed number. In order to divide, we want to make it into an improper fraction. 2 times 16 is 32, plus 11 is 43/16. And now I'm also going to change this into multiplying by the reciprocal in the same step. So times 1/2. 43 times 1 is 43. 16 times 2 is 32. So 43/32, or 1 and 11/32. Now, I wanted to do this one out the long way to show you that it can be done with the whole number, but it doesn't have to be. I could have just ignored the 1 inch on here, trying to find what's between those. I know that whatever is between those is going to have a whole number of 1 inch. All I really needed to do is find what was between the two fractions, the 5/16 and the 3/8. Changing those to 16ths gave me 11/16, and then dividing by 2 would give me 11/32. And then just put the 1 back in front of it. I can do that over here. I'm going to ignore the 2 over here. I'll just put the 2 back in front when I'm done. So I'm going to find what's between 1/4 and 9/32. So I'm going to add those together. Common denominator is going to be 32. So 4 times 8 makes 32. So 1 times 8 is 8/32. And the 9/32 stays as it is. 8 plus 9 is 17/32. And then we divide by 2. 17/32 times 1/2, the reciprocal, gives us 17/64. So the number that is between those two is 2 and 17/64. Any questions on those? Yes, sir.
Instead of doing all that, could you just times the common denominator by 2 and get the same answer?
Yeah, dividing by 2 and multiplying by 1/2 are the same thing. So multiplying by 1/2 just multiplies that denominator by 2. That is correct.
That get the same results all across the board?
Yep. And that is one thing. You'll see a lot of the stuff, I will show you the long way of doing it. But once you get into practice, the shortcuts are everywhere and you'll see them. Don't hesitate to use them. Especially, you're going to have stuff that you're going to use all the time, and you'll see shortcuts like that that'll make it shorter. Please use them. My goal in here is I'll show you the long way, but hopefully I'll try to explain to you how it works and why it works so that you can evaluate those shortcuts when you see them and decide if it's one that's going to work or not. But yeah, in practice, there's a lot of stuff that I'm going to show you that you're going to shorten up so that you can do it a lot quicker on the job. That's for sure. Okay, so today I want to come back and talk a little bit more about the powers and roots. These are classified together as exponents. Now, the basic exponent, the power, has two parts to it. We see something like this, 8 to the power of 3. And we've seen that enough that we all know that that means 3 8s multiplied together. 8 times 8 times 8. Which comes out to be 512. Well, that exponent has the two parts, as we said. The 8 is called the base. That's the number that this exponent is acting upon. The 3 here is called the power. That's telling us how many times that base is repeated in our repeated multiplication here. Now, 8 times 8 times 8 isn't too hard to do on the calculator for 8 to the third power. But we get into higher powers, we don't want to have to be doing that repeated multiplication. If I gave you 2 to the power of 11, you don't want to try to punch that in as 2 times 2 times 2 and try to keep track, did I hit the 2 10 times or 11 times or whatever. You want a shorter way to do that. It's going to be 2048, by the way. So how do we enter that in the calculator? Well, your calculators have one of the following keys. Most Texas Instrument calculators have this key. It's called the caret key. It's your power key. They call it the caret key because it kind of looks like an upside down carrot. It's from the shift 6 on your computer keyboard is where it comes from. Other older Texas Instruments might have a key that looks something like that. Casios and Sharps, most of them have something that looks like this. X with a box there. Or some yet have 2 boxes like that. All 4 of those keys, no matter which one you have, operate the same way. If I want to enter 2 to the power 11, I enter the 2. You press whichever key it is that you have and then enter the 11. And then hit equals or enter. And it should spit out the 2048. So any of you, I want you each to try that and let me know if it doesn't work for any of you. I think most of you have already got it done. Okay. So I want you to try this one. 5 to the power of 6. Get 15,625. Perfect. Now we said powers and roots. The other side of the exponent scale is its inverse. You know, we said every operation we have comes with what we call an inverse. You know, we talked about addition and subtraction. What does it mean to have an inverse? Well, one operation's going forward, the other operation's going in reverse. With addition and subtraction, if I pick a number, let's just say I pick the number 11, and I add 6 to it, I get 17. Well, if I want to get back to the 11, I take that 17 and I subtract 6. I'm back at 11. Adding 6 and subtracting 6 reversed each other. In fact, the opposite is true. If I started with the 11 and I subtracted 6 to get 5, if I wanted to get back to that 11, I would take my 5 and add 6. Gets me back to 11. Here, subtracting 6 and adding 6 again reverse each other. It doesn't matter what order they're done in, they reverse each other. They're opposites or inverses. Multiplication and division work the same way. If I have 12 times 3, I get 36. If I want to turn that back into a 12, I take my 36, I divide by 3 to get 12. Multiplying by 3 and then dividing by 3 reverse each other. If I had started with the 12 and divided by 3 first to get 4, if I wanted to get back to the 12, 4 times 3 gives 12. So again, dividing by 3 and then multiplying by 3 reverse each other. Doesn't matter what order they're done in. Every operation we do in math is reversible. We said 8 to the power of 3 is 512. If I want to reverse that, I use a root. Now, we're all familiar with the square root symbol, or we call it the square root symbol. Its technical name is actually the radical symbol. If it's written like this with no index, it's just a square root. But here I'm not trying to reverse a square, I'm trying to reverse a power of 3. So I put an index in there. A root has two parts again. It has our base, just like a exponent, the power does. And instead of a power, it has an index. That index tells us what power it is that we are reversing. So this is called a cubed root or a third root of 512. It is asking us what number to the third power gives us 512. All we know, we just did 8 to the third power is 512. So we know that that equals 8. So the big question is, where is that third root key on your calculator? For many of you, it's right above that power key, whichever key we had for the power up here. It's a second function in most cases. On the Texas Instrument, it's above that caret key, and I believe it's either an X root, looks something like that, or an N root key. Depending on your calculator, the way that key works is you enter the 3, then you have to do second or shift, depending on your calculator. And then that X root or N root key, some of you it might just be a radical with a box like that, maybe even another box inside of it. Then enter the 512. And when you hit equals, you should get 8. Give you guys a chance to enter that, see if it comes out to 8 for you. Is there anybody that did not get it to come out? Perfect. Well, let's bring in the negatives. Let's look at negative 7 squared. Well, we know that negative 7 squared means negative 7 times negative 7. And we know that a negative times a negative is a positive. 7 times 7 is 49. That has to be a positive 49. However, when I enter this in the calculator, I have to be very careful. One of the more common mistakes in my pre-algebra class, where they do a lot more with powers than what we do, is that exact function right there, squaring a negative. If I just enter the negative key on my calculator, is right down here. That's the negative key. Some calculators allow you to use the minus, the subtraction key. Most of them have a separate negative key that you have to use. So I enter negative 7 like that. If I just do negative 7 and then hit the power key to square it, it gives me negative 49. That's because the calculator does a very strict order of operations. An order of operations says a power happens before a negative. So it squares the 7 and then it applies the negative. So in order to square a negative number on most calculators, we have to put that negative number in parentheses. Now, by the way, when I'm just squaring, I'm not going to use that power key anymore because most calculators have a shortcut key for x squared, for just squaring. But anyway, putting that negative 7 in parentheses then allows my calculator to do it correctly to get that 49. Well, because of that, because squaring a negative number is always going to be positive, what happens if we try to take the square root of a negative 25? Well, a lot of people want to say, well, that's just negative 5. But be careful. Remember, what this is asking is, what number squared equals a negative 25? Well, anything times itself, a positive times a positive will be positive, and a negative times a negative will be positive. There is nothing that I can put in here that when I square it's going to give me a negative. So the square root of negative 25, if you're punching your calculator, it'll tell you an error. I'll most likely say domain error. There is no solution. In the real numbers, we cannot take the square root of a negative number. Now, I qualified that with in the real numbers. If you were to go on to a 4-year degree and get into like a college algebra class, in college algebra, they get into what's called imaginary and complex numbers, where literally they make up a solution for the square root of negative, and then they build a whole portion of algebra around that. For our purposes, can't take the square root of a negative number. That's just the way we're going to do it. If it's a negative and you got to square root it, the answer is no solution. Just be very careful before you write down that there is no solution, that truly is a negative number and it wasn't a calculation error that got you there. The only place really in practical applications that I know of where those negatives, square root of a negative, is actually used in a practical application is in electronics, where you have inductive capacitive circuits and you're trying to look at phase angles and stuff like that. That's the only place, the only application I know of where square rooting a negative is actually a real thing in application. So you guys shouldn't have to do it. Well, let's take negative 5 to the power of 3. Again, make sure you put it in parentheses. Well, negative 5 to the power of 3 is negative 5 times negative 5 times negative 5. Well, negative 5 times negative 5 is a positive 25. But then we have to take that positive 25 times another negative 5. Positive times a negative is a negative, and 25 times 5 is 125. I'm going to keep going here. I want to show a little bit of a pattern. Negative 5 to the power of 4 is 4 negative 5s multiplied together. Well, we know that these first 3 multiply to make negative 125. We just did that up here. Negative 125 times another negative 5. Well, negative times a negative is a positive. 125 times 5 is 625. Let's do that. Negative 5 to the power of 5. Now it's 5 negative 5s multiplied together. Again, we know the first 4 multiply to make 625. That's what we just did up above. Well, 625 times another negative 5. A positive times a negative is negative again. 625 times 5 is 3,125. If we look at this, we might see a little bit of a pattern developing. Let's throw the negative 5 to the power of 6 on here to cement it. So that's 6 negative 5s multiplied together. And again, we know that the first 5 multiply to make negative 3,125. So we multiply that by another negative 5, and negative times a negative is a positive. 3,125 times 5 is 15,625. Now the pattern I was hoping to establish here is very evident here. You can see that the odd powers are the ones with the blue solutions, and the even powers are the ones that have the green solutions there. Well, all of the odd powers gave us negative results, and the even powers gave us positive results. And this is true no matter what number we put in here for the base of our power, of our exponent. If we're starting with a negative number, no matter what negative number we put in there, I should say, that a negative number to an even power is always going to be positive. A negative number or even a positive number, any number to an even power will be positive. Obviously, a positive number to any power will be positive. A negative number to an odd power will be negative. Now, the consequence of that is when we go to do our roots. You know, we saw up here that there was nothing that I could square to get negative 25. So the square root of negative 25 could not be done. However, the third root of a negative 125, we just saw right here that negative 5 to the power of 3 is a negative 125. So the third root of a negative 125 is just a negative 5. But when we get to the fourth root, the fourth root of a negative 625, well, it can't be a positive 5 because positive 5 to the power of 4 is a positive 625. But it can't be a negative 5 either. We just saw here negative 5 to the power of 4 is also a positive 625. There is, once again, no solution here. As we continue down, though, the negative 3,125, if I do a third root of that, not a third root, I should say a fifth root. Well, we just saw that negative 5 to the power of 5 is negative 3,125. So the fifth root of negative 3,125 is just negative 5. And for the sixth root here of negative 15,625, well, again, we just saw that negative 5 to the sixth power is a positive 15,625. So there is no negative number that we can take to the sixth power because any negative number to an even power will always be positive, there's no solution to this as well. So because of that idea that a negative number to an even power is always going to be positive, that means when we do a root with an even index, like 4 or 6, or even just a square root, we cannot take that even root of a negative number. There's no solution to that. No negative number to an even power will give us back a negative. So let's take a look at some examples here. Mix in some order of operations with it. And let's say we're going to calculate to the nearest 100th. Now, first thing I should note, when I say calculate to the nearest 100th, or I want my answer to the nearest 100th, that does not mean we round every calculation off to the 100th as we go. We want to keep every calculation to at least one digit past that. And usually I recommend that you keep it 2 digits past to where you round. So 100th is 2 decimal places. We're going to keep all of our calculations out to 4 decimal places until we get to the final answer. So now here we have this fraction bar, which is an enclosing symbol. So we're going to have to do everything on top of that fraction bar first. So I'm going to write that off to the side over here. Like that. Well, in there we still have another enclosing symbol, the 12 times the 0.4, which is 4.8. Now that takes that parentheses down to a single number, so I can take the parentheses out, remembering that I have to put that squared on there. Now I have 4.8 squared, which is 20, we'll just do it here.
23.04.
Yep, 23.04, perfect. And 18.54 plus 23.04, which is 41.58. So the whole top of this is 41.58. Now let's do the bottom. On bottom here we have a radical. The square root of 2.25 is 1.5. Then we're going to multiply 68 times 0.08, giving us 5.44. 5.44 minus the 1.5 is 3.94. So the bottom of this is 3.94. So let's rewrite this. So we've got the 9.6 up front, plus, in our fraction bar, we got 41.58 on top and 3.94 on bottom. Before we can add, we have to do that division. 41.58 divided by 3.94. Giving us, I'm going to round that to 10.5533. We said we wanted our answer expressed to the nearest 100th. That would be right here. Notice I'm keeping that calculation 2 digits past. So now last step is to add those two, 9.6 and 10.5533, which is 20.1533. And now we will round it to the nearest hundredth. So that's 20.15. Any questions there? Well, let's look at a little bit of an uglier one. So inside our square root, we've got 32 divided by 8 plus 9.34 over 14.7 times 3.14 minus the square root of 43.1 plus parentheses 8.48 divided by 1.6 minus 3.12 squared. So again, we have the enclosing symbol here. The radical of the square root serves as the enclosing symbol. So we go inside there. Well, inside there we have another enclosing symbol, the fraction bar, telling us we have to do what's on top first. Well, what's on top is this. That radical is an enclosing symbol, but it encloses the whole portion on top. So let's work inside there. We've got the 32 divided by 8, which is 4. We add the 9.34 to get 13.34. Now we have to take that square root. The square root of 13.34 gives us 3.6524 is what we're rounding that off. So that's the top here, is 3.6524. On bottom, we have this enclosing symbol here first, the square root, so we're going to work inside there first. Inside there, we have another enclosing symbol, the parentheses, so we're going to start inside there. In there, we got the division, 8.48 divided by 1.6 gives us 5.3. And then we have the 5.3 minus 3.12, which is 2.18. Now we got that parentheses down to a single number, the 2.18. It's squared. I'm going to do that all at once. I'm going to remove the parentheses and I'm going to square it to get 4.7524. I'm going to add those inside the radical to finish off the square root. That's 47.8524. Now I'm down to a single number inside the square root. I can get rid of the square root, but I actually have to do the square root. So the square root of 47.8524 is 6.9175. The square root is gone now. We're back to doing the rest of the problem. No more enclosing symbols, no more exponents. We'll multiply here. 14.7 times 3.14 is 46.158. minus 6.9175 gives us 39.2405. So that's what the whole bottom equals. So what we have here now is the square root of 3.6524 on top over 39.2405. We're going to do that division. 3.6524. Now I'm going to show you a trick on these calculators. Rather than do divide and then have to type in the 39.2405, I do hit divide, but rather than typing in the number, I hit second answer. That's telling the calculator to use the previous answer that's displayed up above. I get 0.0931, we'll call that. And I have to take the square root of that. Second square root. I could do the second answer again, but because I rounded it, I'll just type it in. 0.0931 is 0.3051. To the nearest hundredth again, if that's what we're going to keep rounding to, that's 0.31. Now, yes, I realize you throw in the decimals like that, that gets ugly. The same thing happens when we throw in fractions. You know, we might have 1 2/3 plus 2 1/2 over 3 1/4 times 2/5. It gets ugly, but it's just order of operations. We have to add these two numbers on top. 1 2/3 plus 2 1/2. To make it short for us, I'll just add them here quick. That's 4 1/6. 1/6, not 16. On bottom, we do the same thing. We multiply the 3 1/4 times 2/5. Oh, what is that? 26/10, I believe. And then you'd have to divide. The 4 1/6 you'll make into an improper fraction. That's 25/6 divided by 26/10. Is that really 26/10? It is. No, it can reduce. Sorry, that's going to be 13/10, not 26/10. And then, of course, you'd flip that over and multiply by the reciprocal. 25/6 times 10/13. And you do your cross canceling and multiply and reduce. Okay, I feel like I've babbled on long enough today, so I'm going to give you guys your homework. Your homework today is actually out of the big book. In that book, it is page, there's actually going to be 2 pages, 153 to 154. That should be labeled exercise 3-19. Problems 1 through 37, the odd. Then also on page 155 through 158, it's labeled exercise 3-20, 1 through 13, the odds. Any questions?